Good evening. My name is Law Soo Ken, and I'm a chemical engineering student who is currently in Year 4 Sem 3. Today, I'm going to talk about a topic of polyvinyl chloride as polymeric material.
Again, this is my presentation topic, polyvinyl chloride PVC as polymeric material. Before entering the main description, I would like to share some brief history about PVC. The material was inadvertently produced in 1872 by German chemist Eugen Baumann. The synthesis was later attempted by Ivan Ostrominclensky and Fritz Klatter in early 20th century for its usage in commercial product, but they are suffering from manipulating the mechanical properties of PVC, such as its rigidity and brittleness. Advanced version synthesis was then patented by Voldor Zaman and B.F. Goodrich Company, which they were able to plasticize PVC. The usage of PVC is then widespread until today. The monomer of PVC is known as vinyl chloride. It consists of vinyl group named for double bond carbon, followed by one chlorine atom as substituent. The polymerization of vinyl chloride enables the double bond to be liberated, and the monomer will start linking with each other, eventually forming a bulk chain of macromolecules with repeating number in a typical range of 700 to 1500. As per the nomenclature, the name PVC was given based on the source name. IUPAC has suggested another name, which is known as poly-1-chloroethylene. PVC is highly noticeable in our life. You can see it while you are repairing your pipes, swiping your cards, tying up ropes, stepping on floor, closing a door, shopping in Uniqlo, or even driving. So, if it is in any way, which means the analysis of PVC can be actually pretty simple. A plastic card with magnetic stripe is analyzed using Fourier transform infrared spectroscopy to determine the functional group of the raw material. The material will absorb infrared radiation at each wavelength and get excited. When the electron recombines to its original valence energy level, the quantized energy released is unique for every functional group. Thus, the molecules will be vibrating at different frequencies across wavelengths. At the end of the analysis, infrared spectrum will be obtained and identification of comprised material can be done by matching with the library database of the analysis in software. This is the card that was used for analysis, and this is the FTIR instrument. Before the analysis began, the probe and the metal plate was cleansed using 60% alcohol, followed by the background radiation test run with nothing under the probe. Then, the card was placed under the probe with the probe contacting the card. After the scanning, the infrared spectrum for plus card was obtained as shown here. The peaks represent different vibrational signals from different functional groups. For the slides I have sent last week, I have forgotten to put this FTIR table, my apologies. So, based on this table, the type of functional group can be predicted. I have arranged the table according to the order of the peaks represented here. The stretching here is predicted to be the alkene or alkane group. The fluctuating signals here is believed to be the background radiation exhibited by carbon dioxide in ambient air. The sharp peak, 1731.5, has matched with aldehyde. The sharper peak here is estimated as carboxylic acid. The two peaks here are sulfone groups, and these small stretchings after 1000 cm are believed to be in the range of amine group. Here comes the spikes again, less than 1000. This is predicted to be the disubstituted transalkene, and the rest of the strong stretchings are representing halo group of CCl. The reason I would say this is CCl instead of CBr is because the maximum wave number for CBr is 690. But the spike here has already exceeded this number. Nevertheless, there is a small bending found here with the reading of 537.34, which is under the range of CBR. The estimation using FTIR table merely identifies the functional group rather than telling the actual compound, as one functional group could yield countless amount of compounds, and also compounds with more than one functional group might exist. To further identify compounds, the matching of infrared spectrum with library database in the software has become necessary. The results show polyvinyl chloride has the highest percentage of matching. This has ascertained the fact that main ingredient to make magnetic stripe card is PVC. It is followed by polyethylene, vinyl acetate plus vinyl chloride, and several polyvinyl-based polymers. These compounds are believed to be the flawed and undesired compound during production of PVC. Lastly, sodium bisulfate in KBr and ABS polycarbonate number 1 are also matched. These compounds are believed to be the additives concocted upon the production of plastic cards. To view a material, the stability and degradation studies must be fathomed in order to improve the longevity of a product. The effect of heat and high energy radiation on a polymeric material is a necessity on precautionary measures in order to realize its stability potential. The most apparent type of stability descending phenomenon, which can be observed by naked eye, is thermal degradation. It has a mechanism involving the elimination of HCl in the form of hydrogen chloride, then forming hydrochloric acid when contacting with ambient water vapor. It begins when chloride atom breaks free from its polymer chain, forming free radicals which later attack the polymer. This will lead to the formation of HCl and leaving double bonds on the polymer chain. This mechanism is often referred as dehydrochlorination of PVC, and it usually starts from 100 to 250 degrees Celsius. Polymer chains containing 6 to 7 conjugated bonds are colored, meaning the degradation of PVC comes along with discoloration, and it can be observed by naked eyes. The temperature range for dehydrochlorination of PVC is said to be the first region of thermal degradation. As the temperature raises to a range 250 to 350 degrees Celsius, the polyene will decompose to a lower molecular weight compound. This can be described as a sign of polymer chain cracking. The decomposition of PVC can go further when the temperature exceeds 350 degrees Celsius. It is said to have entered the third region, and a large amount of low molecular weight compound will be formed. The figure shows the pyrolysis of various polymer with respect to its reduction of weight percentage upon thermal degradation. PVC has the lowest thermal stability, amongst others, due to the presence of defective PVC structure, such as tertiary chlorine and head-to-head structure. The long chain of PVC has increased the potential of becoming polyenes, as there will be more carbon atoms available to form radical sites. Heat stabilizers such as lead, barium cadmium, and tin carboxylates can be added. Photooxidative degradation of PVC is another stability descending phenomenon which is worth studying. Consider that its fact happens to be the exposure of PVC to UV light. Long-term exposure to sunlight has become the main lead of PVC material to degrade. While most of the pure plastics are unable to absorb radiation, the impurities or catalyst residues have become the UV receptors, granting the PVC chain to be excited and forming polyene radicals and chlorine radicals. In the presence of oxygens, the free radicals form oxygen hydroperoxide that can break the double bond of the backbone, eventually leading to a brittle structure. Additives, namely Additives namely such as triazoles are used to improve stability of UV exposure. So, these are the examples of degraded plastics. The chair outside the restaurants such as Mamak, the water pipes, and the pails in the garden. These are all caused by long-term sunlight exposure for which the colors are vanishing. Last but not least, in order to produce a magnetic stripe card, vacuum forming technique is used during the production. The polymeric material could be in two forms, PVC pellet or PVC sheet, depending on the manufacturing skill of a production plant. If the process begins with PVC pellets, extrusion technique would be required to produce PVC sheets, then only proceed to standard process of plastic cards. If manufacturers wish to keep the production scale as moderate as possible, they could purchase the made plastic sheets as a retrenchment to avoid a challenging process in extrusion. So this is a hand-sketched process flow diagram of extrusion technique. PVC pellets are fed to extruder continuously, and the extruder will start to melt the pellets with proper temperature and pressure control. The materials now will flow through the mold and die to acquire the sheet, the desired shape. After that, the materials will be cooled in a long constructed cooling zone, and it will be conveyed to die cut machine area for proper sizing. Eventually, the finished product, which is now the PVC sheets, will be sent to packaging and ready for selling. The PVC sheet will then be used as raw material of plastic cards. The desired printing patterns are designed using computer, and the PVC sheet will be fed continuously for printing. From now, I would like to show a footage about PVC printing.
Right after the printing of the computer patterns, the magnetic stripes will be applied on the PVC sheets as follows. The vacuum forming technique is shown here, but lamination is a more appropriate term to be used considering the plastic sheets are relatively thin. The laminated sheets will experience high pressure punching for a better adhesion of printing. Eventually, the sheets will be cut into pieces with a standard sizing of 85.6 mm times 53.98 mm. As you have always seen in your daily life.
So this is the brief flowchart of the production of plastic cards with magnetic stripes. And thank you so much for paying attention to my presentation video. Have a nice day. Bye.